Hello everyone, I am Shkurta Agashi and today it is my pleasure to present our paper on detection of artifacts in ambulatory electrodermal activity data. Mobile and wearable devices such as wristbands are nowadays commonly used to track people's physiological parameters like heart rate and electrodermal activity. Electrodermal activity represents the physiological arousal of a person during an activity, and it has been widely used to infer people's behavior such as affective states, sleep quality, cognitive load, and the quality of social interactions. Recent advancements in ubiquitous technologies allow continuous and unobtrusive measurement of electrodermal activity data in real-world scenarios. However, such data is seriously impacted by a major issue, the presence of artifacts, which are caused by the recording procedure, by environment temperature, as well as body movements. Thereby, automatic recognition of artifacts in ambulatory electrodermal activity data is crucial for humans' behavior detection systems to not only clean the data, but also to avoid making conclusions in spurious data. And this is the goal of our paper. Existing approaches in identifying artifacts in electrodermal activity data include visual inspection, which is cumbersome and very time-consuming, signal processing techniques, which distort the signal and make genuine physiological responses resemble artifacts, or vice versa. Existing automatic approaches have mainly been tested on data collected in a specific setting or from a specific demographic group of users. And all of the existing approaches do not consider the impact of contextual information for this problem. Thereby, in this paper, we present our approach on identifying artifacts, and we propose to use multiple sensors, not only electrodermal activity, but also skin temperature and acceleration. We collect a data set completely in the wild from 13 participants, which include students, teachers, as well as researchers. We collect around 2,000 hours of this data, and 2 human annotators annotate 100 hours of this data set. We make both data sets publicly available. We then also compile a list of guidelines and a dashboard in order to enable researchers to manually label artifacts if it is needed. Both of these tools are available in the following link. In order to analyze the data, we follow common signal processing and machine learning steps. In particular, we first filter the signal to remove a noise. We then decompose the signal into the phasic and tonic components. We segment the data into 5-second windows, and we use these windows from both the mixed electrodermal activity signal as well as the phasic components as an input to the classification pipeline, which is composed of the feature extraction, and we extract 3 types of features: statistical, peaks, and wavelets features, which are then used as input to different classifiers, to linear and nonlinear classifiers, as well as ensemble and deep learning methods. We then resample the data using the random undersampling technique in order to combat the imbalanced data set. We rescale the features using the min-max scaler, and we evaluate our approach by leave one subject out as well as leave one day out validation techniques. We also tune the parameters of the best classifier using a grid search. Our main findings show that from the different classifiers that we investigated, we obtained the best performance using ensemble methods, in particular gradient boosting techniques. We then compare our approach with the random classifiers, and we find that we achieve a recall of 98% for artifacts identification, which is significantly higher than the random guess classifier, and this increment is 42% percentage points. We then achieve an accuracy of 97%, which outperforms the biased classifier that always predicts the majority class. The increment is by 30 percentage points. We further compare our approach with existing approaches in the literature, and we show that state-of-the-art approaches do not generalize well for in the wild data, even after manual adoption. We then train and test existing approaches using our data sets, and even in this case, our approach outperforms existing ones by 8 percentage points. We further quantify the impact of artifacts, body movements, and temperature change in electrodermal activity signals. And in particular, we observe that EDA features that are commonly used to detect humans' behavior are impacted by the presence of artifacts, change in temperature environment, as well as physical activity level of the user. Thereby, we propose a new metric, the EDA quality index, to quantify the overall quality of EDA signals based on these 3 factors: the artifacts, the temperature change, and body movements. For more details, please check out our paper. Thank you for your attention.